Ever been, totally lost somewhere new, and then bam, your phone map just figures it out and guides you.
Oh, yeah. Or maybe you've seen those incredible 3D characters in games that look almost alive.
Exactly. And underneath a lot of that digital magic, there's often this fundamental thing called a mesh.
That's it, mesh data structures. They're really the essential building blocks for how computers represent pretty much anything 3D or spatial.
Okay, so let's really dig into this then. For this deep dive, we want to unpack what these meshes actually are, why they're so important, especially in design, and how they link up to bigger ideas in computational design.
And we got some great source material to help. We're looking at bits from a lecture video, 2025 Data and Design Class '07, lecturemesh.mp4, and also a document called Design and Mesh Data Structures, which is originally in Korean.
Right. Both seem to give a really detailed look at meshes, specifically from that computational design angle.
Yeah, they do.
And for you listening, getting your head around meshes is kind of like finding a shortcut. It helps you grasp how computers actually, see and work with spatial stuff.
Totally. Whether you're just curious about tech, or maybe you're a designer, or you're trying to solve problems with data, understanding this is, well, it's pretty relevant.
Our goal here is really to pull out the key insights about meshes from these sources,
Yeah.
make these ideas, which can seem complex, feel a bit more accessible, maybe even engaging.
Absolutely. So maybe we should start with that foundation. Computational design. When people hear that, they might immediately think of, like, specific software or coding, right?
Yeah, that's what I assume, like Grasshopper or something.
But the sources suggest it's actually broader than that. It's more a way of thinking.
A way of thinking. How so?
Well, the lecture really emphasizes it's the conceptual approach. It's
Hmm.
about tackling design problems through data, not necessarily tied to one tool. One source puts it like computational design.
It's a concept, right? Yes,
Yeah,
a concept, a way of thinking. Ah, okay. So it's less about the tools and more about the strategy of using numerical data for, like, precision and efficiency, moving beyond just intuition.
exactly. It's that strategic shift. But then, of course, you need a way to actually implement those ideas.
Right. And that's where programming comes in, I guess. It
Yeah.
sounds like it's not just helpful, but pretty much essential in this field.
Oh, definitely. The lecture hammers this point home. Programming is the language you use to talk to the computer in design terms.
Like an artist needing to know their brushes.
Precisely. It's
Uh,
how you realize the concepts. The lecture even uses this really vivid analogy, comparing programming skill to driving a tank in the Hosan dynasty,
right.
while others have, less advanced tools.
Wow, okay. So it gives you a serious advantage.
It really does.
Yeah.
So if computational design is this data-driven way of thinking and programming is how you execute it, then we need ways to represent that spatial information digitally.
And that leads us to the basic building blocks.
Exactly. The lecture lists the fundamentals. Vectors, points, curves, surfaces, and of course, meshes. These are like the vocabulary for describing space in the computer.
Got it. Vectors, points, curves, surfaces, meshes. And it's interesting, the source mentions that for a computational designer, the data structure itself, the way you organize that data, can actually be the output.
That's a really key point.
Yeah.
It's not just the final visual thing. The underlying structure is part of the design. And this is where meshes connect to other ideas like graphs.
Graphs, like network diagrams.
Sort of, yeah. The lecture points out that graphs and meshes are basically the same at a core level, because they both use nodes or points and connections between them. In meshes, we call those nodes vertices.
Okay, so a mesh uses vertices points in 3D space and connects them. But how is that different from, say, a smooth, continuous surface I might model?
Ah, that's the crucial difference. It comes down to discretization.
Yeah.
A mesh is fundamentally a discrete data structure.
Discrete meaning, broken down.
Exactly. Think of it as information chopped up into distinct pieces. For meshes, those pieces are primarily triangles. So unlike a perfectly smooth mathematical curve, a mesh represents shape in these separate defined steps.
So it's an approximation using lots of tiny flat triangles to represent a potentially curved surface.
You got it. And the core definition is just two things. A set of vertices, the 3D coordinates, x, y, z for each point, and the connectivity.
Connectivity being.
Basically the instructions, like a list saying, okay, vertices 1, 5, and 7 make up the first triangle, vertices 5, 8, and 7 make up the second, and so on. It tells you how the points link together to form faces.
And that simple structure, vertices and connectivity. That's why meshes are so widely used. The lecture mentioned pretty much all 3D software uses them. SketchUp, Max, Maya, even WebGL.
Absolutely. That simplicity is its strength for universality. Because it's just points and connections, it's a really basic standard format. Different programs don't need complex translation, they just consume that vertex and face list. As the lecture says, mesh is the primary data structure for the universal uses.
Makes sense. Easy data exchange.
Yep, it streamlines everything.
So this whole process of taking something continuous from the real world, or maybe a smooth mathematical shape, and turning it into these finite computable pieces, that's discretization again.
That's the core idea. The lecture puts it really clearly. In the end, we have to change the infinite into the finite, change the continuous into the discrete. That's fundamental.
Like pixels in a digital photo, taking a continuous scene and breaking it into a grid.
Perfect example. Or
Oh.
finite element analysis and engineering, breaking a complex object into a mesh of simple elements to simulate stress. It's all about making the infinite manageable for a computer.
Okay, so we have the basic mesh structure, vertices, connectivity, triangles, but you mentioned it can hold more info.
Oh yeah, much more. The mesh acts like a container. You can attach data to the vertices themselves.
Like what kind of data?
Well, vertex color, for instance.
Yeah.
Or texture coordinates the UVs that tell the software how to wrap a 2D image onto the 3D surface.
Ah, like putting a texture map on a character model?
Exactly. And you can store normal vectors too.
Neural vectors. What do they do again?
They define the orientation, basically which way each face or even each vertex is pointing outwards. Super important for lighting and rendering.
Right, so the computer knows how light should bounce off it.
Precisely. You can even store analysis results directly on the mesh, like stress values or temperature.
Wow. So it becomes this really rich data package, not just a simple shape.
Exactly. And the way those vertices are connected, the topology tells you fundamental things about the shape itself, beyond just its geometry.
Topology, like whether it's a solid object or has holes.
Yeah, things like that. The connections reveal properties like the Euler characteristic, which relates the number of vertices, edges, and faces, and can tell you if it's topologically like a sphere or a donut, for instance. It's about the structure, not just the exact coordinates.
Fascinating. And you mentioned normal vectors for orientation. Are there different kinds?
You generally talk about face normals, one vector perpendicular to each triangle, showing its direction, and vertex normals, which are often averaged from the surrounding faces to give a smoother sense of direction at each point. Both are critical for rendering.
And the source mentioned something about estimating curvature from the mesh.
Yeah, briefly. By looking at the angles between adjacent faces meeting at an edge, you can get an approximation of how curved the underlying surface is at that point. It's clever how much you can infer.
It really is. Now, for a mesh to represent something, well, physically sensible, I guess, does it need special properties?
Often, yes. We talk about manifold meshes. That's a key concept for like 3D printing or simulation.
Right, manifold. What does that mean?
It basically means the mesh is nicely connected, like a proper surface. Technically, it means every edge of the mesh connects exactly two faces.
Ah, so no weird situations where three or more faces meet at one edge, or edges that are only part of one face, leaving a hole.
Exactly. It ensures the mesh represents a closed, watertight, or consistently defined surface without topological errors. Think of it as being well-behaved.
Okay. Now, if you have a huge mesh, like from a 3D scan or a complex simulation, just dealing with millions of triangles must get slow.
Oh, absolutely. Searching or interacting with that raw data is inefficient. That's where spatial partitioning techniques become really important.
Ways to organize the data in space.
Precisely. To divide and conquer. The lecture mentions a couple of key ones, quad trees and octrees.
Octrees, I think I've heard that in relation to video games. For performance.
You probably have.
Yeah.
An octree is for 3D space. Imagine putting your whole scene inside a big cube. If there's too much stuff in it, you divide that cube into 8 smaller cubes.
Okay.
And you keep doing that recursively for any smaller cube that still has too much complexity until each little box has a manageable amount of data.
Like a hierarchical filing system for 3D space?
Exactly like that. So if you need to find objects near the player, you only check the octree cubes they're currently in, and maybe the immediate neighbors, instead of searching everything.
That makes total sense. Much faster. The lecture actually highlighted the problem without it having to check your mouse click against potentially all the points on screen.
Right. It avoids that brute force nightmare. It's about efficient querying. You can also use octrees for things like voxelization, turning geometry into 3D pixels or voxels.
Interesting. Any other partitioning methods mentioned?
Yeah, it also briefly touched on Voronoi diagrams and Delaunay triangulation. These are more about partitioning space based on proximity to a set of points.
Voronoi, isn't that where you get those cell-like patterns?
That's the one. Each point gets a region around it containing all locations closer to that point than any other, useful for analyzing density or surface areas. Delaunay triangulation is related, creating a nice triangulation between points, often used for terrain generation.
Okay, so lots of ways to manage complex spatial data. Now, going back to the mesh structure itself, the basic vertex face list, the source called it a bit dumb.
Uh-huh. Yeah, dumb in the sense that it doesn't explicitly store much about neighbor relationships. A triangle knows its vertices, but it doesn't inherently know which triangle is next to it along a given edge.
Ah, I see. So finding neighbors requires some searching.
It can, yeah. And for more advanced operations, especially things like mesh editing or preparing models for fabrication, you often need richer connectivity info. That's where structures like the half-edge data structure come in.
Half edge, how does that work?
It's more complex, but way more powerful. Instead of just edges, you think of each edge as two directed half-edges pointing opposite ways.
Okay.
And each half-edge stores pointers, links to useful things.
Hmm.
The vertex it points to, the face it belongs to, the next half-edge going around that face, and crucially, its opposite, or twin half-edge.
Wow, that sounds like a lot more information packed in there.
It is. It lets you very quickly navigate the mesh surface, find adjacent faces, vertices connected to an edge, faces connected to a vertex. All those relationships are explicitly stored. It makes complex algorithms much more efficient.
So if you needed to, say, smooth a mesh or prepare it for 3D printing with specific edge treatments, half edge would be much better.
Definitely. The lecture notes it's a well-defined, well-documented data structure, ideal for those kinds of tasks where topology traversal is key.
Gotcha. So standard meshes are simple and universal. Half edge is smarter but more complex. How do these compare to, say, B-rep surfaces used in CAD?
Good question. B-reps, or boundary representations, define shapes using mathematical surface patches, often NURBS surfaces, stitched together. They're great for defining smooth, precise curves and surfaces, especially in engineering design.
Easier to manipulate initially, maybe.
Often, yes. But the lecture points out a potential issue.
Yeah.
Sometimes are understood mainly as these sort of rectangular panel constructions. And managing very complex B-rep models or exchanging them between different software can sometimes be tricky.
So what happens then?
Very often, for analysis, rendering, simulation, or even just data exchange, those complex B-rep models get converted into meshes.
Ah, so the mesh becomes the common currency again.
Exactly. Even if you design with smooth surfaces, the mesh is often the format used for downstream applications because it's discrete, easily processed, and universally understood.
It really hammers home how central meshes are, and the range of applications listed in the sources is huge.
It really is. 3D modeling for games, movies, VFX, that's obvious. But also engineering simulations, processing 3D scan data, the perception systems in self-driving cars.
Self-driving cars use meshes.
Well, they process point clouds and often generate mesh representations of the environment to understand it. Also, digital fabrication like 3D printing relies heavily on mesh data, and geographic information systems, GIS, for mapping.
Wow, it's pretty much everywhere digital meets physical space.
And getting more important as computing power grows, allowing us to handle bigger and more complex meshes.
So, given how fundamental this all is, the lecture also had some advice on actually learning this stuff effectively, right? It wasn't just about memorizing definition.
No, definitely not. A key point was about connecting new information to what you already know. Don't learn it in isolation. Try to build analogies or see relationships.
Makes sense. Build on existing knowledge.
Yeah. And practice, especially with coding. The advice was basically, coding is difficult at first with repetition. After doing it once, you can just look at it, meaning that initial hurdle is tough, but practice builds familiarity quickly.
Get your hands dirty, basically.
Exactly. And the other big piece of advice was collaboration. Ask questions. Talk to people. Ask each other about things you don't know. That's how you improve. Learning isn't a solo sport.
Really good advice. Okay, so as we start to wrap this up, what's the absolute core takeaway? If someone remembers only one thing about meshes, what should it be?
I'd say that meshes are the fundamental discrete way computers represent 3D shapes and spatial information. They're built from simple vertices and connections, but this structure is incredibly versatile and underpins a massive range of digital technologies we use every day.
So next time you're navigating with your phone map or playing a game or even seeing a cool architectural rendering, you can think about the underlying mesh, that web of triangles making it all work.
Definitely. And maybe a final thought to leave you with. Now that you have this basic idea of how digital shapes are built, how we discretize reality,
Yeah.
what new possibilities do you think this opens up for creating things, for interacting with information, for blending the real and virtual? What comes next?